Good morning, everybody, dear colleagues and dear friends. It's a great pleasure and honor to welcome you to Athens and to this 2025, the 15th International Conference on the Dependable Systems, Service Technologies. We're especially grateful to our many colleagues who have traveled all over the world, but especially from Ukraine, during a very difficult period for your countries and for your daily lives. Your presence with us today, it's not something we take for granted. It's an act of strength and hope, and it shows a deep commitment to science, education, and collaboration, even under the most demanding circumstances. This conference is more than a scientific event. It is a community. It is a place where we share ideas, we build a new collaboration, and support each other as colleagues and as human beings. We hope that Desert 2025 will offer you not only inspiration of your work, but also the feeling that you are not alone, that this international community stands by you. I would like to sincerely thank all of those who work to organize this conference, our speakers and contributors, and all of you for being here and sharing your time, your knowledge, and your experience. With these few words, I declare this 2025 official opening, and I have to thank you all your contribution and all your participations in our conferences. Thank you very much of you. First, I'd like to invite for a small welcome one of our contributors, co-organizer, Professor Kakaroudas, Director of Department of Informatics for Medical Applications of University of Thessalia. Professor Kakaroudas. And of course, President of Presentation from IEEE as Vice Co-Chair.
Thank you very much, Professor Bardis. Well, dear organizers, dear researchers, dear participants, it is such a great pleasure for me personally to participate in the 15th International Conference on Dependable Systems, Services and Technologies. It is also worth mentioning the fact that IEEE Greece section technically sponsors the conference, showing once more its focus on science and research that unite us all. This conference is organized by respected colleagues. I had the pleasure to meet you all in the past, and these colleagues originate from academy and industry, whom I want to thank and congratulate for their hard work. They delivered a high-quality technical program despite the ongoing war in Ukraine, where the conference had traditionally been hosted before relocating in Greece, thanks to the attempts and the initiative from Professor Bardis and the Greek colleagues. The Department of Computer Science and Biomedical Informatics consistently supports scientific and research events, conferences, symposia, and places particular emphasis on co-organized events with scientists worldwide. I remember the first time we learned that Desert 2022 would take place in Greece. We became part of it, supporting our colleagues from the Ukrainian section. Here, we are again in 2025, demonstrating our consistent support. I firmly believe that beyond the technical aspects of the conference, this is a valuable opportunity for researchers, especially Ukrainians, to discuss their work and initiate collaborations, enriching the European research ecosystem and providing a second home for our fellow Ukrainian researchers. As the head of the Department of Computer Science and Biomedical Informatics, I would like to greet the conference organizers, the respected authors, and the participants, and wish you productive and insightful work at your conference. Thank you very much.
Thank you, Professor Kakaroudas. It was very pleased for you that all these years you support our conference with your advisors and, of course, with IEEE Greek section. Thank you very much for your contribution. I think that together with us is also the Dean of Hellenic Army Academy, Professor Kaimakamis. He was before, but he had to go because today is a special day for Hellenic Army Academy. It's the official welcome of the first cadets, and everybody now is on the parades on our university or academy, and he sent his greeting to warmest welcome to all of us, and of course Hellenic Army Academy is supporting as University of Thessalia and Professor Kakaroudas this marvelous desert conferences. After that, we have to continue with Professor in co-chair of our conference, Professor Harchenko. Please.
Is it working? It's my to join open session of the 15th special conference, Dependable System Services and Technologies. I have to end the national university.
Good morning. It looks like we have lost Vladimir. Vyacheslav.
Yes, I think it's pure internet connection. Sorry.
Dear colleagues, actually, we continue our plenary meeting, and now there will be the actually information from the rector of our university
Dear colleagues,
with greeting.
participants of the 15th International Scientific and Technical Conference on Dependable Systems, Services and Technologies, the third 2025. I have the honor to congratulate you on the opening of the conference, which brings together scientists, engineers, students, lecture specialists in one of the most promising and sensitive areas of information technologies and dependability and security. This year's Desert Conference theme, Trustworthy and Resilient AI Systems for a Safe and Secure World, is especially important for us, representatives of the National Aerospace University Kharkiv Aviation Institute, which is called the Frontline. Indeed, our university campus has been hit more than 200 times by shells, missiles, drones during almost 4 years of war. But despite so many hits, we continue and intensify our educational activities, research, and technological developments. This is, in our opinion, true resilience, the resilience of the university infrastructure and its employees. We are proud that the co-chair of the conference, together with its founder, Professor Vyacheslav Kharchenko, for the 4th year in a row, is Professor Nicholas Bardis, a representative of the country and unique and beautiful cities that have been so loved and respected in Ukraine since ancient times. We are very grateful to the Greek section of the IEEE Society, the Hellenic Army Academy, personally to its leadership, and to the so organized of the Desert Conference for their excellent collaboration. It provides an opportunity for young scientists, PhD students, and experienced professors to prepare and deliver reports on the problems of artificial intelligence, cybersecurity, and mobile technologies, discuss them, and prepare joint progress for security and quality life. The conference will be 20 years old next year, and we are very proud of this wonderful community that has been formed around it. So once again, I wish the conference participants success and creativity of the highest quality, and we look forward to seeing you in our wonderful city after the war.
Okay. Dear colleagues, we continue our plenary session after invitation rector of our National Aerospace University, and it's our pleasure with Professor Nicholas Bardis to present some historical pages of our conference, and I very shortly present our welcome presentation.
Yes, thank you. Yes, thank you, Professor. Perfect.
Okay, dear colleagues, welcome to our conference. The theme of this conference: Trustworthy and Resilient AI System for Safe and Secure World. And I would like to say a few words about history of our conference. First, the third conference was held in Poltava about 20 years ago in Military Communication Institute. And so we have some history with military universities. And after that, four conferences were held in research and production company Radi in Ukraine. After that, we held our conference in Sevastopol, the Sevastopol Institute of Banking. Next year, we held our conference in Kiev, Харьков, Chernivtsi, and other Ukrainian cities. Beginning in 2019, we held our conference in United Kingdom in Leeds Beckett University, and come back to Kiev and Kharkiv. Beginning of 2022, began our Greek era of the desert, and thank you very much our Greek colleagues for possibility to hold this conference in the beautiful, unique city Athens. Short statistic about the Desert 2025. We received more than 200 papers, and 140 papers was preliminary accepted for presentation, but review process will be continued later. We have participants which represent more than 20 countries. The key topics of our conference is cybersecurity, safety, resilience, AI, cloud computing, mobile and robotics technology, Internet of Things, aerospace and aviation, mobile system, UAV-based, energy grid, health system, and so on. We will have 5 plenary sessions, 9 topical sessions, and 6 workshops, and 1 round table. I hope and I sure that all these sessions and workshops and round table will be very interesting, and it will good possibility to discuss the most important and interesting topics in area safe, secure, and resilient computing. It's my pleasure to represent. It's our pleasure to represent our keynote speakers. Dr. Yannick Fourastier, Dr. Christopher Spirito, Professor Christos Xenakis, Dr. Yannis Agadakos, Professor Petra Haverkorn, and Professor Maria Dorash, and Professor Andrzej Rusiński. Sorry, but we need to remember Dr. Professor Ted Kochanski, Tadeusz Paul Kochanski. Ted a lot of time participate in our conference, but in August this year he died, and he was very important participants on our conference a lot of time, and we will talk about Dr. Ted Kochanski research results on our workshop in our round table, and now we will can say an eternal memory. It's our pleasure to thank once more organizer of this conference. First of all, the host Hellenic Military Academy, Athens, University of Thessaly, Lamia, Greece, and of course our National Aerospace University as founder of this conference, Leeds Beckett University, United Kingdom, Lutsk National Technical University, Ukraine, and of course our colleagues from IEEE Greek section. We thank all members of committees, partners, and sponsors of our conference, and all participants who joined to our conference. Thank you very much for your attention, and welcome to Desert 2025. Yes.
So we continue with with our program, with Professor Yannick Forster for his keynote as a keynote speaker on the title of his work on trustworthy autonomy of cyber physical system. Professor Yannick Forster, based on the United Kingdom, he's currently Senior Director of Technology Group at Ghent, and brings experience from previous roles that he had at Aegis, on Thales, and Code Europe. Please, Professor.
Good morning, everyone. So I am indeed just a little correction. I'm not belonging to Code Europe. So this conference, this talk and speech are in the context of my works in the context of Code Europe. But I am based indeed in the UK. So nice to meet you, everyone. Let me show you my screen so I can provide you with this conference. Is it okay? Yeah.
Yes.
Like. Good. So good morning and thank you for being here that early. My name is Yannick Forestier from Code Europe, a technology company that is developing in Ukraine since 2019 with labs working quite closely with HAI. I'm very honored to on the stage for this opening keynote for this 2025. Last talk, last speech I gave in this on this stage was in 2021, and this talk, in fact, is in the continuation somehow to my speech I gave at that time. That was about assurance levels for intelligent decision-making systems embedded into cyber physical systems. Today, I will be trying to keep raising your attention on this topic I am bringing to the share with a keynote that is about the trustworthiness engineering for high-risk AI systems. It's connected to previous works in 2022 I presented then was in Harkiv, last Harkiv desert. This keynote is also accompanied by a paper. So what I am presenting now in this speech, you will find it also in the paper. Well, more in details with quite more context, my bibliography for that keynote as well, reused from also other research papers I have been introducing and presenting this year. So I am diving, what I want today is to put a focus on trustworthiness engineering, and I will be speaking partially about what I sometimes call physical AI, that is artificial intelligence embedded in cyber physical systems, advanced robotics or distributed swarms, as many of you, particularly in HAI, know to work on. Where decisions made by machines can directly influence the physical world. And this is very the key aspect. When without any more
your slide is not switching.
Is not showing my screen?
It shows the screen, but do you change the light? Oh, now it's changing the lights. Yeah. Okay, you can continue from the slides that you're speaking, okay, because they're not changing. Okay.
Okay, so I have organized my talk here in 4 sequences. First, how current regulatory and policy frameworks in distinct jurisdictions implicitly define AI trustworthiness, and whether those definitions are converging. For that, I have limited and focused my studies on the regulations in the EU, in North America, the UK, and Singapore. Second, what AI governance means when we look at the full life cycle of high-risk systems as defined by the EU AI Act, typically, and how a specific trustworthiness chapter should look in practice. Third, assurance levels and how we can move toward a practical framework for engineering trustworthy autonomy. Fourth, I will close with an initiative agenda on trustworthy autonomy we are developing with a few of colleagues in the room, also other specialists and very experts in Europe. So altogether, we are composing the scientific committee for this initiative. I am introducing you in this keynote. Before we dive into the situation and the perspective I am bringing today, let me give you a quick look at where my work originates. At Code Europe, we build systems that operate in the field, edge controllers for unstable grids, autonomous assets under adversarial conditions, critical infrastructure with no fallback. And in every one of these, AI is not optional, it's embedded. So the context here is not academic only. It is operational, high stakes, and very real. I am working on that since already 2 decades myself in diverse contexts, and it's been already quite central in my research since years for my PhD already. What I just outlined as a technical imperative when introducing verifiable trust at runtime is also fast becoming a regulatory necessity. The EU AI Act that has been finalized in 2024 has come into force from this year. And it imposes strict obligations on AI, on high-risk AI systems. So AI that is embedded into systems carrying high stakes. And particularly the algorithms that are embedded in critical infrastructure. This is, you will tell me, okay, but we are already doing that since 40 years, 50 years, since we are controlling systems with software. Yes, indeed, but all this time, the software was stable, not changing all the time by itself. Let's examine then how these regulatory requirements align with AI now system life cycle stages and why existing tools fall short of ensuring compliance. Self-adaptive mechanisms are increasingly embedded in real-world control systems, particularly in these sectors where decisions carry very high consequences. Over the last few years, AI has moved inside the control loops of real systems. We now see learning components in protection schemes of power grids, in railway traffic management, in industrial automation, and even in defense systems. And of course, in various forms of autonomous vehicles and robots and drones and so on and so forth. These systems sense, decide, and act in open environments, often very close to people and critical infrastructures. Here, I illustrate with an utility. So, considering the example of that utility substation, AI here models, they are supporting critical decisions. They are forecasting the load from what they can observe on the microgrid they are answering to or balancing. And simultaneously, they are identifying anomalies in real-time sensor data and to correct and to adjust and to react in a smart manner. Nothing new, you will tell me. Yes, indeed. Just the algorithms are changing. And here we are with the context of many possibilities of AI techniques. The very power of AI is introducing new kinds of risks. If these models behave unexpectedly or errors propagate throughout the control loop, the resulting impact may include equipment damage, safety hazards, or widespread service interruptions. Mind what did happen in Spain last June. A blackout over all the peninsula. That's why maintaining strict control over the AI behavior, what we call the trust boundary, is essential in such contexts. And you will tell me, yeah, but we are already doing that with dependability and safety. Yes, right. But here we are beyond the so-called safety, so-called dependability. And we set here the stage of understanding how trustworthiness must be engineered, measured, and enforced across AI systems deployed in safety-critical domains. At the same time, we have heard a lot of talk about trustworthy AI, or AI safety also. There are ethics guidelines, principle lists, and marketing labels. Beautiful principles. In many deployments, however, trustworthiness remains an aspirational label, a magic claim. And this is it is a problem. They are far from being systematically engineered, evidenced, and enforced inside the host system. The very real problem there is when things go wrong, as everyone in this room knows. The DSAT community has a long history with safety, reliability, dependability, security, and so we know that when you want to trust a critical system, you do not rely on slogans. You need a combination of rigorous engineering, structured evidence, and a clear assurance argument. My central claim here today is that we now need to bring this culture to AI-enabled autonomy, and in particular to high-risk systems. Because the word trustworthiness is used in many different ways, we need to be precise about what it can mean here in a rather technical sense. The general idea is to get a justified belief about the behavior of a system in a given context. Not blind trust, not unconditional trust, but a belief that is supported by evidence and by a coherent argument. And we know to do that. I frame this using this 4-layer conceptual stack. At the top, there are the trust concepts. This is where philosophers, ethicists, and social scientists remind us that trust is not the same as reliance, that trust involves expectations, vulnerability, and sometimes power asymmetries. This layer also includes the various attributes that appear in guidelines such as safety, robustness, fairness, privacy, and so on. The second layer consists of norms and regulations. At this level, abstract ideas are turned into obligations, principles, rules. For example, the way of the EU Act defines high-risk systems and their obligations, or how the NIST AI risk management framework describes trustworthy AI properties and the risk processes. The third layer is system architecture. This is where you decide which functions will be handled by AI components and which will not. Where you put safety monitors, how you structure human oversight, and how you implement trust envelopes around the AI and the system. The fourth layer is technical assurance. Here, you have testing, formal analysis, simulation campaigns, monitoring, incident investigation, and so on. They produce the evidence that can support or refute claims about behavior. Trustworthiness engineering means keeping these 4 layers coherent. Claims at the top must be traceable down to the design and evidence at the bottom. Evidence at the bottom should be interpretable in the language of obligations and concepts at the top. With this notion of trustworthiness in mind, let us look at how these 4 jurisdictions that I've been talking about are functioning. Europe has the AI Act, which has now entered into force. It sets up a risk-based regime and defines a specific category of high-risk AI systems. For those, it imposes obligations along the life cycle. There must be a risk management system, data, and data governance measures, technical documentation, logging, transparency to users, human oversight measures, robustness and cybersecurity, and post-market monitoring even. This is binding law with market surveillance and sanctions. You can even withdraw the system. And so to bin investments. And this is critical for any kind of industrial or public authority. The UK has taken a different path. Rather than a single horizontal AI law, there is a set of cross-regulator principles, and regulators are expected to apply them within their existing mandates. The government emphasizes a pro-innovation approach, what means nothing, in fact. I am in the UK. Coordination across regulators, what means in the UK, honestly, do nothing. And the use of guidance and regulatory sandboxes rather than detailed technical rules. It means industrials, do your job and we'll see. And this is where I am stepping in, because I cannot accept kind of situation where all the issues can be on my shoulders and everyone is away the situation apart the day there will be a problem and they will be looking after me. This is not feasible, and any kind of scientist, technologist can accept that. In North America, the US NIST has published the AI risk management framework a pair of years ago. The document is explicitly non-regulatory. It is a voluntary framework, but it is already widely used as a reference for sector regulators and industry bodies. For the same reason, I have been just commenting about the UK. We cannot accept to have all the load on our shoulders, and we need safeguards. This RFM from the NFC defines trustworthy AI characteristics and describes functions such as govern, map, measure, and manage. Singapore was quite early in 2020 when they published their Model AI Governance Framework, which is now in its second edition. It includes very practical guidance about internal governance structures, operations management, human involvement in AI-augmented decision-making, and communication with stakeholders. Singapore also created AI Verify, a testing framework and toolkit that combines process checks and technical tests to generate governance reports. At the same time, there are important divergences and gaps. One major difference is about the legal force. The EU AI Act is binding, with fines and the possibility to withdraw products. At 180 degrees, at 180 degrees, the NIC framework and the Singapore model AI governance framework are voluntary, although they are influential. The UK approach is non-statutory, relies on regulators to interpret principles. This means that the same system may be under very different levels of compulsion depending on where it is deployed. And as an industrial, when I am creating a system, a technology, it's not meant to be only on an island market. It's meant to be sold also in various geographies. There are also differences in how general purposes models or foundations models are treated. And these are still evolving. That has significant implications for any architecture that relies on a foundation model inside a safety relevant function. Sector coverage also varies, and some domains remain under-specified. Defense applications, and we are having quite a lot now with robotized systems for defense, they are often excluded or carved out from the horizontal AI legislation, which means they are governed by separate, sometimes classified rules. Critical national infrastructure is often covered via safety or cybersecurity regulation, but AI-specific expectations are not always clear. AI is software, but not any software, and this is where is the point. Robotized swarms and very large multi-agent systems are hardly mentioned at all, despite their potential for emergent behavior and reconfiguring and even recoding themselves in life. For physical AI systems, this means that we cannot simply derive a full answer from the legal texts. We must interpret, align, and sometimes anticipate. This points directly to the need for internal AI governance and for trustworthiness engineering. They provide a translation from high-level regulatory language into systems-level design and evidence. So let me turn to AI governance now. For a pragmatic definition, AI governance is the set of structures, processes, and resources that guide, control, and oversee the development and use of AI systems in line with legal, ethical, and organizational objectives. In other words, it is the organizational connector between obligations and engineering practice. It includes the obvious elements such as committees, policies, and guidelines, but that is not enough. It also includes workflows, quality gates, approval rights, audit trails, and escalation paths. It matters who can approve the deployment of a new model, who can decide to roll back, and who is allowed to override the AI. For high-risk AI systems, governance also has a very concrete responsibility. It must ensure that the evidence needed to support trustworthiness claims is generated, aggregated, and reviewed. That must happen both before deployment and throughout operation. This is not a single ethics board. It is a distributed responsibility embedded across the life cycle and across disciplines. The easiest way to see this is to look at the life cycle of a high-risk AI-based system. So here we back with to our well-known playground of the V model. At the requirement stage, governance should ensure that high-risk use cases are correctly identified and that explicit safety and trustworthiness objectives are formulated. For some use cases, governance might decide that AI is not appropriate at all. and arbitrate, no algorithms, self-learning there. During design and architecture, governance needs to oversee how functions are allocated to AI and non-AI components. It must ensure that human oversight is designed in, that trust envelopes and fallback modes are specified, and that any enforcement modules are given authority in the control path. In the data and model management phase, governance has to define and enforce policies for data collection, cleaning, labeling, privacy, bias analysis, quality. It must also control which models can be trained, how they are versioned, and under which conditions they can be promoted to integration or production. Verification, validation, and assurance are not just technical activities. They are also governed. Governance bodies should define criteria for adequate testing, approve test plans, and accept or reject residual risks. That's very usual, very common. We are doing it for safety since decades. During deployment and operation, governance sets rules for monitoring, incident reporting, change management, and decommissioning. Business as usual. For learning or frequently updated systems, here, governance must say when an update is considered minor and when it triggers a new approval cycle. This is like what we do since also 2 decades for all the cybersecurity matters in this kind of software-dependent critical infrastructures. This life cycle perspective is very close to what we know from functional safety standards, but extended to data and AI components. This brings us naturally to the interaction with existing dependability standards and AI-specific frameworks. Same situation we have faced or found in the early 2000s when safety and security have been converging. I have been myself working on the ED 200 definition, the standard on aeronautics systems by the EASA to secure the aerospace systems. And we are meeting the same situation today, 25 years later. In many sectors, mature standards already exist that structure assurance practice. Now, today, think of the ISO 26262 for automotive functional safety, the EN 50126 series for railway, trams, and signaling, the ARP 4754 and the 4761 documents for the aircraft development and system safety, and more recently, model-based safety and dependability analysis guidance. These standards define safety goals, integrity levels, hazard analysis methods, and sets of techniques that are expected for different criticality levels. They already embody a certain notion of assurance levels, even if they do not always use that expression. On the AI side, we now have frameworks such as the NIST ARMF and methodology like AMLAS for assurance of machine learning in safety-related systems. They focus on AI-specific risks and evidence. For example, data management, machine learning hazards, machine learning specific testing, etc. AI governance for high-risk systems must integrate these two worlds, not run them in parallel. The same function should not have one safety argument, a separate security argument, and then an unconnected AI ethics statement. That would be confusing for regulators, but a nightmare for internal decision makers in practice when we are developing a system or operating it. Instead, we should aim for integrated assurance cases in which AI-specific evidence is woven into system-level safety and security arguments. That integration is exactly where many of you in this room with experience in safety cases and dependability can bring a lot of value. Let me now talk about trustworthiness, engineering, and metrics. In classical safety and reliability engineering, we do not only say this system is safe in a qualitative sense. We measure or estimate failure rates, reliability functions, coverage, and so on. We use those to support the argument that a system will meet its safety objectives. For AI, especially learning-based components, we need the same discipline. High-level attributes such as robustness, fairness, transparency are not helpful if they remain vague. They must be tied to more concrete indicators and tests. So I suggest at least 6 families of metrics that matter for high-risk AI. Robustness metrics describe how performance behaves under perturbations, unusual inputs, or adversarial conditions. Reliability metrics capture stability of performance across scenarios and over time. Explainability-related metrics try to quantify the quality or stability of explanations, although this remains quite a difficult, challenging topic. Data governance metrics track provenance, labeling quality, representativeness, detection of data drift, model drift even. Security metrics reflect susceptibility to adversarial attacks, data poisoning, and similar threats. Oversight metrics try to characterize how effective human supervision actually is. For this to be useful, tests and metrics need to be organized and associated with specific system configurations and operating domains. This is where platforms like Storm come in. Storm is a modular test bench that we have designed to orchestrate missions and scenarios, execute specialized tests, gather metrics, and aggregate them into trustworthiness artifacts for AI-enabled edge systems. And for this, we are articulating with one of the persons in the room, Alexei, in ХАІ. The important point is not the tool itself, but the pattern. You systematically measure the aspects of trustworthiness that matter. You attach those measurements to specific system versions and contexts, and use them as part of the assurance argument. Metrics alone are not enough. We also need a way to summarize and communicate how much assurance we have for given function. This is where assurance levels come in. Many of you are familiar with safety integrity levels or automotive safety integrity levels, where a combination of severity, exposure, controllability leads to different required rigor of development, verification, and validation. The level is not a probability of failure, but a proxy for how much effort and which techniques have been applied. A few years ago, I proposed an assurance level framework specifically for decision-making in autonomous intelligence systems. So systems relying on themselves to self-decide how to proceed next. The idea was to define classes of decision functions, for example, advisory decisions, supervisory control, or direct control, and to associate them with different intensities of analysis, testing, and monitoring. The same work, presented in DCERT 2021, also introduced the concept of trustworthiness service level agreements, where you specify at runtime what level of safety, integrity, or resilience is guaranteed and under which conditions. In a harmonized trustworthiness engineering approach, assurance levels for AI would be defined in such a way that they can be mapped to both sector standards and AI-specific frameworks. For example, if you have an AI-based perception function in an autonomous vehicle, a high assurance level might imply evidence consistent with an SLD classification, supplemented by AI-specific robustness metrics and uncertainty management. In another domain, the same assurance level could align with expectations in the EN 50/129 expectations and have its own set of required techniques. The point is that assurance levels would create a common scaffold across domains and technologies. Even with assurance levels and strong pre-deployment evidence, we should not assume that the story ends at deployment. I illustrate here with a case scenario in a VPP controller. A VPP is a virtual power plant. It abstracts real utilities to balance the grid more securely. Learning-based systems and even non-learning AI systems operating in open environments, they can encounter situations that were not fully covered in testing. They may also degrade over time, for example, because of a sensor is aging, there are changes in the environment, or deliberate attacks, cyber attacks on the utility. Don't think this is a dream or imagination. This is happening every day in Ukraine. For that reason, runtime mechanisms are also needed so that the overall system keeps ensured to remain within a trust envelope. Similarly, a safety envelope, the trust envelope, is the range of behavior that is considered acceptable with respect to safety and mission objectives. In there, we are close with what is worked at AI safety. In earlier work, I described the trustworthiness module that monitors the state of the system and its environment, computes how close it is to safety boundaries, and constrains the decision-making subsystem accordingly. It can trigger degraded modes of safe states when necessary. More recently, we have been working on FORT with IMT in France, so Mintelecom, a runtime enforcement system for AI components. Conceptually, FORT sits in the control path between the AI output and the actuators. It ingests policies and configuration derived from storm assessments and enforces constraints on the AI output. Some constraints are hard bounds. For example, certain actions are simply forbidden, or control signals must stay within specified ranges, specified regions of functioning. Others relate to timing, explainability, or even privacy. At a kind of AI system, it means the model not to leak internal knowledge. During operation, FORT monitors both the AI outputs and relevant system states and applies these rules in real time. It also logs enforcement, events, and incidents, which then feed back into the next assessment cycle, in addition to provide the authorities with visibility.
Professor, we have less than 10 minutes. Okay.
Yeah, I'm reaching the end soon now.
Thank you.
So this conceptual stack, or with this conceptual stack, Storm lives mainly in the technical assurance layer, while Fort lives at the interface between architecture and assurance. And together, they support integrated design, time, and runtime assurance. Now, stepping back and looking at the broader picture. In this talk, what you will also find in my paper is that I argue that trustworthiness engineering for high-risk AI systems needs at least 4 ingredients. First, an awareness of the regulatory landscape so that we understand not only abstract principles, but concrete obligations and proof expectations. Second, governance structures and lifecycle processes that connect these obligations to engineering practice. Third, an engineering discipline around metrics, assurance levels, and enforcement that can handle AI components in physical systems. And fourth, tools and patterns that show this is not just theory. I gave Storm and Fort as the illustration of one such paper, such a pair. And there are, of course, other approaches. However, methods, vocabularies, and case studies remain fragmented. This is what I see, I meant there. Today, we are with silos, and what we need is a convergence hub. Work on AI safety is often living in a different community than work on robotics, which in turn is separate from functional safety, cybersecurity, or policy research. And this fragmentation makes it harder for regulators and practitioners to see the full picture. And it slows down convergence on effective practice. So that convergence hub I am introducing and proposing. For physical AI, indeed, the situation is not sustainable. We need a more integrated view of trustworthy autonomy. So, to help address this, we have launched a collaborative book project on trustworthy autonomy. The idea is to assemble a volume that brings together foundations of AI trustworthiness, regulatory and policy perspectives, engineering methods, cybersecurity challenges, and domain-specific case studies for mission-critical cyber-physical systems and advanced robotics. The book is intended to serve 2 purposes. One is as a teaching reference. We want something that can support a course or a module on trustworthy autonomy for engineers, computer scientists, and maybe even lawyers, and to teach them in quite a standard manner what trustworthy autonomy is. In a world where the machines are soon not needing us anymore to decide whatever they are doing. So this autonomy should be trustworthy, and we need to engineering it. Second, therefore, is a practical reference for practitioners and regulators who have to design, assess, or approve high-risk AI systems of this kind. The structure mirrors some of the elements I have covered today. There is a foundation part, a part on regulation and governance, a part on engineering methods and assurance levels, a part on cybersecurity and safety interactions, and a set of domain case studies, for example, in energy, rail, aerospace, and defense. Section heads, so Professor Vyacheslav Kharchenko and myself as coordinators, but also with Carsten Thoma from Berlin's Advanced Applied Science University, Professor Hakima Chaouchi in Paris at the IMT, George Soikov in Bulgaria, and others. We are already constituting this scientific committee. And we are actively looking for chapter authors, especially for case studies that show real-world trustworthiness practice. So my hope is that this community today will see this as a useful focal point, and that some of you will consider contributing. Let me close with a few messages. First, for high-risk AI systems, trustworthiness cannot be an optional level. It has to be engineered, evidenced, enforced in a way that is compatible with both engineering practice and regulatory expectations. Second, there is an emerging convergence in how major jurisdictions speak about AI trustworthiness. They all emphasize safety, robustness, transparency, oversight, accountability, and life cycle documentation. At the same time, they differ in legal force and coverage, which means organizations must take responsibility for how they implement these expectations. Third, AI governance and assurance level are a bridge between regulation and technical practice. They link obligations to metrics, architectures, and tools. Without this bridge, we will either overregulate by fear or under-assure by overconfidence. Fourth, platforms such as Storm and Fort are examples that this kind of trustworthiness engineering is feasible. They are not the whole answer, but they show a way to organize evidence and enforcement for AI-enabled components to be deployed at the edge. This is where we are working. Finally, the Trustworthy Autonomy Initiative and the book projects are an invitation. If you are working on methods, tools, or case studies that could help others build or assess high-risk AI systems, we would very much welcome your involvement. I will be happy to discuss afterwards, and you can also reach me by email or Professor Václav Hartsenko to connect on these topics. So thank you for your attention, and I look forward for your question in the remaining time.
Thank you very much, Dr. Froster, our friend Yannick. It was very useful, your lecture, and you raised a lot of questions nowadays with AI and all these philosophical questions that you give. How is the future? Have we any questions, please? Please raise your hand or take the word or write to the chat.
Here's the chat.
Okay, let's start me. I have a small question. I wrote it also to the chat so everybody can show the questions if they couldn't listen it. The question is if AI system is in safety critical domains, can one day monitor, explain, and justify their own behavior by themselves? Who or what is behind them will ultimately hold the authority and the responsibility? The system itself, by itself, the designers of the system, or we as the society of institution? What is your opinion for the future of that?
So first, that's not the future at all. This is already today, I would say. First, because the system, critical infrastructure, you need to monitor it. And when you are designing the system, you are already designing also the monitoring system that will be watching this critical system. So it is already today. This is the first thing. The second thing is the size of the problems and at what level of responsibility we are talking. And that's why the governance organization is very important. What I did say in my keynote is that responsibility is very distributed. And if we do not want to lose who is liable, we need to know, to define who is in front of what. And then, depending on what the case is, there is a microphone here that is providing. Yeah, if you can shut off your microphone, please. Yeah. So what I was saying is that depending on what the size of the problem or what is the nature of the case, then you are escalating to the right level of authority. From bottom level, which is operation of the infrastructure to make it functioning in the safety envelope that has been defined, that is also contracted and ensured with the industrial assurance. Well, the insurances are there to cover some category of damages. And the industrial is deploying the organization to meet with this contractual requirement. And for doing that, it's necessary to have the data from the monitoring system, the logs. And that's why Fort typically I did introduced here, but we already introduced it in several conferences this year. We are generating a lot of logs from whatever is asked to the AI, whatever the AI is producing, or the iteration the internal iteration is producing to get the explainability. So regarding the explanation and the justification of the behavior by the system, we are getting this already available. What we are missing is the semantic of this content for its observation. I did talk about silos of disciplines. Safety is not that much connected with security and so on and so forth. And that's why we need to have a convergence hub on which we are aggregating this monitoring and then dispatching with the correct semantic to the correct audience, to the appropriate audience. And with this integration, having still an issue, then we are escalating to what is the society responsibility need to handle and to regulate or to consider. So there is leveled answering to your question, Nikos, and concretely, we need to keep the human in the loop to supervise what the machine is doing. The machine is there to provide us a service. First, is not to inverse the situation. We are there to serve the machine. And
thank you.
Later on about what is in the industries.
Thank you very much. So we have a lot of work to do as a human beings, huh?
Yeah, but that's why I am calling for this support by the community for producing this reference book we want to publish in the next 12-18 months to fit ourselves, community, with the appropriate grid of reading first. To supply the authorities with what's happening actually in the domain of physical AI, because it is huge changes happening, and these changes are remaining under control. We are having the hands on. We are the technologists. They are not coming from another universe. They are built on Earth by us, the human, and we need to keep that under control. And this, as a community, we need to have a common definition, common tools to work on. So we are bringing on the table some already developing technologies for collecting this, gathering this, but we need also to prepare our capacities next, engineers that we are educating to think correctly these disciplines and to prepare for the next.
Thank you. Thank you very much. Thank you very much. Also, we have a question. Yeah.
Thank you very much for this informative presentation, highly informative, hitting all the right points on the distance between declaration and implementation, the physical operation of these systems. So can we summarize it based on your lecture, the general scope of these systems as this trustworthy autonomy within a certain risk envelope which is acceptable to the society. So for some applications, for some risks, they can allow this autonomy. For others, if human is in the loop for high-risk decisions, so it's not autonomy, technically speaking, because every decision of the system, high-profile, high-risk decision of the system has to be accepted and confirmed by human. So this is a limited trustworthy autonomy, and the challenge here is for us as the developers and the society in general is to develop correct risk profiles for these systems so that we understand which risks are acceptable for us and to the society and which risks are not acceptable, so we cannot allow autonomous systems in these domains. Is this interpretation correct?
Yeah, indeed, this is a correct interpretation, and that's why I have been categorizing the families of risk, because one thing is the performance stability of a system that is actually delivering the service is expected to be delivered when needed, and another thing is the failure that is out of the performance envelope defined and causing damages, which is a safety problem. And these two aspects are, one is reliability, the other one is safety. Even conceptually, they are close, they're not the same. And when we are going to large scale, I'm taking again the example of Spain Peninsula last June. At the beginning is an unbalancing of the grid, wrongly adequated by the systems. And at the end is a massive reliability problem that has happened. And this is the kind of risk class that you have been introducing here. And this is what we need to also work on. When we are taking separately the components, they are working well, they are doing well. But when we are observing the system of system aggregation, what is happening? Are we keeping in the same envelope or not? How are we addressing that in a correct way? And this is why at some moment I have been talking with these multi-agent AI-enabled systems. When we are going at scale, we are in front of multi-agent systems. And we are today not well fit by the regulation to address that. And as a developer community, we need to take that into account in order to set up definitions, organizations, activities that govern this system at scale. In Spain, it's not distributed totally responsibility disconnected. It is at some moment an authority that is supervising the world grid. The same it is in Ukraine. I don't know what is the name in Spain as of now, but in Ukraine, it falls the responsibility to Ukraine to have this supervision in general, if even technically they are not having hands-on everything. But they are the glue, putting all together the things, and each operator at his level is with having responsibilities, tasks, and obligations of information reverting to the authority. and this is in many domains the same. So answering to your question, this is what also we need to clarify to have this large-scale trustworthy autonomy of cyber physical systems under control.
Thank you.
Thank you very much. Thank you very much, Dr.
Someone is mute.
Is listening me. Excellent. Thank you very much for your contribution in our conference, Dr. Yannick. It was very nice, your lecture. Thank you very much. So we'll continue our program with coffee break for some minutes and a notification to the moderators so that they have to log in their sites in the session and to approve who are online. And we can start in 10 minutes, 17 minutes, our conference. Okay, thank you.
Yeah. I just put my email for anyone who is willing to connect on these initiatives we are working.
You can send it in the chat room now so everybody can see, and we will include in our proceedings, book of abstracts proceedings, your emails, so everybody can connect with you.
Thank you.
Thank you, Yannick.